I'm starting second session. In the first session, we explore how to solve classification problem using traditional machine learning methods.
Üzerinden ses gelmedi.
Şu an açtım.
Açtım şu an.
So in first session, we explore how to solve a simple classification problem using traditional machine learning models. And now in this session, I'm going to show you. We are going to dive into the world of deep learning and time series data. We'll just again look at our data. Data is again publicly available on Mendeley and titled with monitoring water quality using digital sensors. It's a timestamp data where the sensors recorded temperature, pH factor, and water turbidity in every minute. So it's were recorded 24 hours from 15th January to 22nd January. And recording rate was one set of data per minute average. But this type of data gives us lots of possibilities, and I'm going to show you how I use this type of data to solve two real world tests using deep learning models called LSTM or long short-term memory. The first step, again, I imported all necessary libraries. The difference between first one and here, it's just TensorFlow Aquaculture. And TensorFlow is for the deep learning model, deep learning components. We have here again pandas, matplotlib, seaborn, scikit-learn, and etc. It will take time to import, and I imported the necessary libraries. Then again, I need to understand my data. I load the data using read Excel function, since my data is an Excel file here. Then the first thing I always do after loading is to verify it works. So I just print the shape of it using the dot shape attribute. Our data has 9,623 sample, 3 row, and 4 features. So then to get first look at the structure of data, I use head attribute, and you see the first 5 rows here. And we have date and time column, temperature column, pH, and turbidity values. Then to get more specific info, I use info attribute. And it's very useful because it shows us that our data doesn't have missing value here, and show also the data types here. So after loading data here in second cell, I begin the main preprocessing. So I just create a copy of my original data to ensure my original data stays the same in case I make a mistake. So I create a copy using a copy attribute, and then rename the columns here. Just rename the columns to simpler lower cases level, date, time, temperature, pH, and turbidity, and print the index of data using index, and print again head of the data using the head function. Yeah, our index, the index of data is range index, start from 0 to over 9600, and you can see the column names is changed. The column names is changed now. Then these are the most important step for every time-dependent data, because I convert the datetime column from string to real to a proper datetime object using pandas library, pandas package, and then set this column as a new index, and sort these indices to ensure canonical order. So these steps give us a powerful abilities, let's say. And for example, we can now select specific samples just using simple steps. Let's say I get this date and time, and right here, and let's say I want to select sample between 4 p.m. and 8 p.m. and I just change this to change the hour value 20 and print this code here, this row, and I can easily get samples. I just try to benefit from and can see it easily. Yeah, you can see we have all samples in specific time range here, and for 4 p.m. to 8 p.m. So another benefit is we can calculate right now easily average of, for example, average of temperature for each day, just using I get the temperature column and then use resample function and with d means here the days, and then get the mean. When I print it, I get the I use temp here. I should use temperature. Change this in temperature. Yeah, now I get the average of I get the temperature average of temperature for each day. You can see 15, 16, 8, 17, and this is the average. And I just change D to H to get our average. And the time object is so powerful because so we need to change something to datetime object. Yes, then I perform here a little simple feature engineering. I added new two column to our data sets. One of them is day and other is weather. So is day, I just check if hour of index our index is between 6 a.m. to between 6 a.m. and 6 p.m. and then I assign 1, otherwise assign 0. So the 1 means day, 0 means night here. In weather column, I start by settings all value to dry. Then I open description of my data, and they wrote here between this row, between this row should be a rainy day. So then I just select those rows, and assign them rain value. So we have now 5, and I just print a shape, head, tail, and info of data. You can see here the process data, and we have now temperature, pH, turbidity is there embedded. We have 1, 2, 3, 4, 5 feature, and date time is our index now. It's no longer a column here, as you can see. And here is the info here's the summary of our data. So I don't want to do any data analysis any further. I don't want to analyze this data further because we already did in session 1. If you want to analyze more, and if you want to plot a graph here, you just go to the session 1 and copy those functions and paste it in here, and you can use them as well. But I don't want to do it because it will take time. So I'm just jump into the model structure and build a model. So my first step is predicting the future temperature. So I just want to use these 4 features. If you want, you can add here the weather features, but I just want to use these 4, and its sensor readings from last 60 minutes to predict single temperature value 15 minutes into the future. I just define here future to use and target to predict. My features are temperature, pH, turbidity is day, and my target is the temperature. So I filter our original data using the selected features, and just create a copy here as a forecast data frame. And I print the head just to show you. Yes, this is our data frame now, our forecast data frame. So we have 4 features and 9,000 over 9,000 samples. So we need to scale them. This is important, very important. In the first session, I used standard scaler, but here I just want to use max scaler. So it squares all value in all value range between 0 and 1. So I use fit transform. I apply fit transform on data frame, forecast data frame, and get the scale data. You can see the shape of it. We have over 9,000 sample and 4 features. Because I'm using the LSTM model, LSTM expect a sequence of data. So I need to create a sequence of data. I defined here a helper function called create sequence 15min, and this function just gets end step in and end step out parameter and data parameter, and this data parameter is obviously our scale data. And end step in, I define here end step in equals to 60, and that means use the last 60 minutes of the data as input. And here end step out means predict the temperature 15 minutes ahead. So the function give me a x and y vector. X is the input, y is the target vector. So it includes a sequence of 60 time step, and then y consists just single temperature value that occurs 15 minutes after this input sequence end. So I use create sequence 15 function here to get x forecast and y forecast. You can see the shape of them. I just print it. So shape of x has x has 9,549 sample, and each sample has 50 time step, 60 time step, and 4 features here. And shape of y is a one-dimensional vector because it has just a single temperature value. So then I need to split them into I need to split them into training test sets. So I can't use here random splitting because it's a time-dependent data. So I use here chronicle splitting. So I just take the first 80% of data for training and the last 20% of data as, for testing. And we see the we can see the shape, training and testing data. For training and testing data, the over 7,000 samples. Train data has over 7,000 sample, and X test has a 1,900 sample. And each one has 60 minutes time series, time step, and 4 features here. So we prepare. So the data is ready now, and we just now we just talk about the model structure. So my model here is sequentially built sequentially, and you just use sequential function to build a sequential model. My first layer, LSTM layer. So LSTM is type of recurrent type of time series model, and it has a memory layer in it, and this memory layer just allow it to remember important information from earlier sequence. So it has here the parameter units called units, and you just, if you want to, you can increase this number. It's just a memory of the LSTM. You write here 128 or 64, but I just use 50 here. And then I use here activation function. I use value activation. So activation function is the most important thing for neural network. So what is activation function? Actually, we talked about earlier in lecture 1 or 2. But I can simply explain. Think of a simple brain neuron. I just open a paint again here. So I just think of a just single brain neuron, and here is the neuron number 1. And we have the second neuron here, neuron number 2. It's really hard to draw without mouse. And let's say the neuron number 1 receives a signal. This is our signal, and its weight, and the signal has a weight of, let's say, 0.8. And if the weight reach the threshold, threshold of this neuron, and this neuron just take this signal and pass to another signal, another neuron. So let's say we have another signal here, and it has a weight of 0.4, minus 0.4. And then this weight doesn't reach the threshold of neuron, and the neuron just passes nothing here. And the rel function is the same. The logic of rel function is the same. I just opens a graph rel function. Yeah, you can see if rel function gets negative value, returns 0, and if it gets positive number, positive value here, it's returned the value itself. So it is very important for a neural network because it introduces nonlinearity. And without any activation function, a neural network model, no matter how deep is, just could learn simple linear relationship. So I just use a rel function because it's the most popular one and it's worked very well. And then give here just a shape of our data, 60 and 4. Here. And we have the dropout layer, and this dropout layer just randomly deactivate 20% of the neuron to prevent overfitting. And we have the dense layer at the end, and this dense layer just condenses all information from LSTM to one single value, one single temperature value here. So this is our model structure. Then I just compile it using Adam optimizer and a mean squared error loss function. So the loss is a metric that the optimizer tried to minimize. And mean squared error just worked by taking the difference between predicted and actual value and just square it and then get the average of it. So it's a simple value. The model's goal is just to make the model's goal is make this loss value as low as possible. So then we get the summary using the summary function. You see here there are model structure, LS3 layer, LSTM, here the 2 layer, LSTM dropout, and dense layer. So then finally I train my model using the fit attribute. I give my train sets and train label, and we have the epoch epoch parameter here, and epoch it's just is complete run to data set, entire data sets. And batch size here, the model just look at the samples in small group of 32. And we have the validation split parameter. The model just split 10% of data for validation. And we have the early stopping. And early stopping, and if the loss value doesn't improve, then it will just stop the training. So I run this cell, and you can see we are training now. We have 10 epoch, so the model tried to minimize this loss value. So we are waiting for this training to end. Yeah, so it ends for 5 epochs. After the 5 epochs, then I just get the prediction using predict attribute. But this predictions value is scaled value, so I need to unscale them. I apply inverse transform here and get the real temperature prediction. So then I get the real temperature prediction and real temperature value, and then just here these are just the plotting function. So I plot the real value and prediction value on the same plot, same graph. So you see here, the blue one is the predicted temperature, and red one is the actual temperature. So mean absolute error for 15 minutes forecast is 0.6, and that means the difference between actual temperature and predicted temperature is 0.6 degree. It's a good prediction, but you can improve this model by just changing the parameter here. You can change. You can change here these parameters 60 to maybe 30 or 2 hours. I use just 1 hour, and you can change to 15 to another value, or you can increase this units number, or increase this epochs or validation speed. So you can try to improve the model on your own. So the second task here is the animal detection. I want to detect unusual spike in turbidity column, turbidity value. So I use just turbidity column here. I filter data frame using turbidity column and just create a copy of it using the copy attribute as an animal data frame. So the logic here is I train a model first on normal data, and then by training, the model learns the fundamental pattern of normal turbidity values. So then when I give the model abnormal data, then the model tries to predict it, but it will fail. It will not predict it. So then give an alarm for abnormal, alarm for anomaly. That's the logic here. So then I just create a new data frame. And before that, I use max scaler to scale the anomaly data frame, and then filter the data using dry days. So here, dry days is our normal data. So I use here again LSTM autoencoder. So LSTM expect a sequence of data. I already called that. And I define here again helper function called create anomaly sequences. And this function is simpler than other because for autoencoders the input and the output are the same, because we want to hear the model don't predict the future, it just try to predict on its value. So we give input as a x vector here, and the output is also the same, and it just train with x vector here, and then predict the x again here. So the function gets n-step parameter and n-step anomaly defined here in 30 using the 30 minutes window to define the pattern. So just look at the 30 minutes window and then predict this 30 minutes window again. So I create the animal sequences here using this function, and you can the shape of it. We have over 8,000 samples, and each one has 30 time step and one value, and this value is 30 value. Here I set seed, because if I again do this analysis after some time, so it has to give a same result. So I define a seed value here, and then now we talk about the sequence model structure here. The model built sequentially again. The difference between this model and the other ones, the first one is just repeat vector here, repeat vector layer. So my first layer LSTM as an encoder. So my decoder layer is again LSTM, and then we have the dense layer at the end. These are the same. And we have just repeat vector layer. So the LSTM needs to expect a time series, a sequence of time. So the encoder LSTM gives just single vector here, single one-dimensional vector. So we need to copy 30 times of this output of that output. So we have to use repeat vector layer here. So just this layer just copy this one-dimensional vector 30 times, and then give it again the LSTM as an input. Here the LSTM as an input. So then we just at the end have a dense layer. Just condenses all the information from LSTM to one value, and this one value is temperature value and turbidity value here. So I compile the model using optimizer and mean absolute error loss function, and get the summary using the summary function. You see we have four different layers: LSTM, vector, LSTM again, and dense layer. So then I train the model. I already talked about this parameter. So it's the same. These are the same parameter. So I start to, I'm just right now I'm training the model, and you can see the model tries to again minimize these loss values. So we are waiting for training to end. We have 10 epochs here, and last one. Okay, 9 epoch. Our loss value doesn't improve anymore, so it just starting to training. It will just start training because we have the early starting function. So I get prediction using the predict attribute again, but this prediction just for the get average of loss values, always loss values. I define a train loss variable, and this variable is just a mean of all the loss variables. So I just use this set a threshold. So I just set threshold using all loss values and taking 99 percentile of all loss here. So if the model, so my model, when my model predicts a value, turbidity value, if the error goes above this threshold, then model gives an anomaly flag, and that's the logic. So I just get the XOR using the query analysis sequence function, and then get predict using my model, prediction value using my model, and then the rest of the code is just for plotting. It's not important here. I get the prediction, and I set my threshold to 0.01. and my model detects 570 anomalies. So you can see I highlighted the rain period as a blue box here, and my model just give alarm before the rain and keep giving the alarm during the rain period, and just stop here after the rain. So you can think that the model just learned the high turbidity value, and when it's high, when it has a high value of turbidity, it's give an alarm. But if you look at this part, you can see we have a high turbidity value here, but the model don't give any alarm here. So this means that our model just learn the normal pattern of turbidity values, and then if you give it a normal value, and then it gives an alarm. So that means our model works pretty well because we don't give any weather information. It just use the turbidity value. So to make this more practical, I create here just with a simulation. So I give information model one by one in real time. And for every minute, I give another value to model. And we have here some requirements. So the model so the model detects, if the model detects 5 or more anomalies and within 15 minutes, then gives the alarm and turn off, if only turn off the alarm if it's see 60 minutes of normal value. This cell a little bit complicated, but I use here just time. I use here start index and end index. So I start from 5 hours before it starts, like here, and end index is 5 hours later. The rain start 5 hours after the rain starts. So just like from here to here, it's my time range here, and I just have a simulation loop here, and the requirements codes and the codes for requirements. And you can see I give the model, I give information to the model one by one in real time, and the model just predict the state here. And now it's giving a alarm state, it's predicting an alarm state here. And you can see the error values here. If these error values goes up our threshold, and then gives the alarm and predict as an alarm here. So we are waiting here for simulation to end. Almost there. Yeah. Simulation complete, and first alarm triggered at 9 p.m. So you can see here the green line is the rain, and green line is the just show us the time to rain start rain, and here you can see my model predicts before the rain as an anomaly here, and then gives another alarm during the rain period. So this graph just shows the error value, and you can see if this error goes above this threshold line, and it gives a number error here. And so our LSTM autoencoder works very well here. Yeah, this is and if you have any question here, the rest of code is unnecessary. You don't look at that part. So yeah, if you have get any error or something, you can ask me. Yeah, this case is solved. Do you have any question?